Hello. Um, Thermal stress. That's actually thermal elongation. I call it thermal elongation. So there's going to be a change in length associated with temperature change. And it's going to be proportional to a constant alpha. I'm not going to require you guys to do this, but I just want you to know about it. Just that like there are seams in bridges. Sidewalks have cracks predetermined. There's like expansion room here and there, all over the world, really. And so this is a pretty important design consideration. Is, depending on, if you put something outside in Phoenix, it might get larger than if you put something outside in, a coastal area. Outside of that, I want you guys to do some really quick chapter 10 homeworks. I really like, the linear deformation stuff. So it's going to be 10-1, 10-3. Okay, and then I'm going to combine that with, here's a pretty picture. Let's do 10-9 too. I showed you that. Yeah, let's do 10-9 as well. So 10-1, 10-3, 10-9. Now we're going to combine that with chapter 11 homeworks. So this is some pretty cool stuff. So I was just saying, elastic modulus is a material property. They give you it. This is how you get it. So if you didn't know what your spring constant was, then you would take your spring and you would measure how much force you're applying in order to get that change in length. And so they have a very rigorous testing method where they form a shape that they call a dog bone, and basically it's right here. So you have threads on the top and the bottom, and then you intentionally make a skinny location in your material, and you're going to precisely measure the dimensions of how long this is and all of these diameters. So, and what you're doing is you're intentionally making a location where you know it's going to fail here. So normally when you pull something until it fails, say it's just clamped like this, it's going to fail. Where's it going to fail when it fails? It's going to fail right at the clamp. But if they carefully design a dog bone, then they know exactly where it's going to fail and not at the clamp, and they can understand that geometry very well. So this is some of the equipment. They took a picture of it. Yeah, pretty cool. So your dog bone's just going to be loaded up in there, and then they're going to need to know exactly how much force they're applying to this press or hydraulic. And so if you have a really tight control of all of this, then you can determine how much force and how much elongation happened. So this is a typical relationship between stress and strain. So you have stress on the vertical axis and strain down here. And 0.05 correlates to 5%, 10%, 15, 20, 25. So this particular specimen failed, I would say right there. So the ultimate strength of the material was over here, 65 KSI, or 450 megapascals. It sounds pretty strong. Now, over here, I really want to zoom in, so I'm just going to draw it. This is crazy important. So there's a part of the curve that's a straight line. This part of the curve is where stress equals elastic modulus times epsilon. So down here is epsilon, here's stress. So the slope of this line, the rise over run, is going to be your elastic modulus. Okay, so this chart is really showing you Hooke's law only applies up to a certain point. And this point is, I call it the yield strength. But through this book, they've called it the allowable limit. So if you push it past 30 KSI, or 30,000 pounds per square inch, then it will start to behave plastically. Okay, and plastic does not mean plastic in the material, like this is freaking plastic. No, plastic is talking about the behavior of the stress strain diagram, and it becomes squishy in the sense where very low stresses will cause much higher strains, and it gets pretty squishy until it hits a point where it's destroyed. And up till here, the dog bone is like necking at some location, and it's getting less and less material there until it snaps, and then it's just meaningless data after that ultimate. And this stuff is meaningful, and it's a little more advanced. I'm not going to need you to know about work hardening, but if you plastically yield, I call this yielding, and then you unload it, it will never return back to its original shape. So the strain will be offset from zero. And so if you've plastically deformed something past its yield, allowable limit, then it will never return all the way back to its original length. So that would be like, if you had Laffy Taffy and you stretched it, it would just be stretch forever after that, so it would have plastically deformed. And I think the book is going to talk a lot about that. So really cool stuff. And every material is different. I am very familiar with how metals behave. It even talks about necking. Very good. Okay. Yep, delta sigma over here, delta E. They even said you can measure the angle and find it. Wow. Right. This is also important. Every material has a different point where Hooke's law is no longer appropriate. And since there's such a wide variety of like behaviors in this area, it's pretty standard to take a 0.2% offset and call this point, wherever it hits on this function, call this point the yield point. So it usually includes a little bit of a bend here. So there's pretty exotic materials like Inconel where it doesn't look linear at all. So like if you were to zoom in, it would kind of look like that the whole way. And you're like, well, where is my elastic region? And so then you just say, oh, take a right there. And then just sort of assume that it's straightish right there. So by the offset method.